So hello everyone, we are going to learn how to delete a node in a B tree. So this is basically just to give you an example to see that how all the operations are done. Already in the theoretical session, in the previous videos, we have already discussed the properties of B trees and how the deletion can be done. What are the required things to be managed? Already we have discussed. Now in this video, we are just having a look at how to delete in a given B tree. So let's start. We are given a tree and these are the nodes to be deleted in the given tree. So um, I believe that you are already aware that in order to work with on the B tree for deletion operation, we need to maintain this condition. Number of child must be ceil m by 2 and number of keys must be ceil m by 2 minus 1. So if the order 4 means uh, the maximum keys that any node can have is 3, and in deletion we have to take care that number of child should be 2 in our case here, and number of keys should be 1, means minimum one key must be there at every point of time. So if you find that when you are doing deletion and this property is not maintained, that means you need to do some kind of merging and splitting in order to maintain it. Now, when we do deletion is actually this is a balance tree and it's order tree. So we already have learned how to delete in the Bunny search tree. So in the Bunny search tree, for deletion, we have three cases. Case one, when we are deleting a leaf node. So when you do insertion or when you do deletion, everything to be done at the leaf node. Okay, though you start from the root node, but when you do insertion, finally you need to go to the leaf and insert a value. Similarly, when you want to delete something, you are actually deleting from the leaf node. So there is a possibility that you want to delete a root maybe or any internal node maybe, which is not actually a leaf. But we know that in the BHC deletion, we are actually proceeding with deleting the successor node or the predecessor node. So we need to stick to one of the root. So in our case, I am going to stick with the left subtree rule. That means whenever we get a case of reading a node which has two child, so if I want to read a node which has two child, I will always uh, pick a substitute from the left subtree. This is what I am doing. So we need to make a decision. We need to first decide that whenever we come across this kind of situation, then how we are going to proceed. So in our example, I am going to proceed with left subtree. So left subtree, when I say that means in the left subtree, I will be going to replace this node with the maximum element, because the maximum element is actually the previous element of this. Okay, so this all already we discussed in our previous videos and lectures. So the first thing is to delete 82. So 82 is this. So I am going to replace it with 80. So 80 is going to come here, and when we bring 80 here and 80, this creates a kind of vacuum here. It creates an empty space here. Now this leaf is actually empty, which is not fulfilling the requirement, because every node must have minimum one key value. This is a no key values, so this is not permitted. So what is required? We need to look to the sibling nodes. So because we are doing left biased operation, so we always from the left side. So we'll see that the left node is not having extra keys that can be passed to fix this problem. Then it will look to the right sibling. Right sibling is having one extra key, because in our case, the minimum requirement is that every node must have one key. It has two keys, so we can take from the right sibling. And do keep in mind that whenever we take a key from the sibling, if it is the right sibling, we take the minimum value. If it is left sibling, we take the maximum key value. So here this is right sibling, so we'll take 85. So means when we say we take 85, means 85 should go to the parent, and this value should go down. So what we get? We get something like this: 20 is here, 6 is here, and then 80 comes down, 85 goes up, and then 90. So 82 is out. It's deleted. Then 20. So 20 is the root node here, and it has two child. So we will be using left subtree method. So that means 20 to be replaced with 10. And when we replace the 10, that means this is going to become uh, vacuum or an empty. So it will look to the sibling to fill this space, means will fix the requirement. So it actually it needs one key here, because the minimum key for every node is one. So it will look to the left sibling, and left sibling has actually extra keys. So it will going to provide one key to the parent, and this will come down. So we have something like this 10, we have 2, 4, this is 5 is here, we have 6 here, we have 78, 25, 80, and 85, and this is 90. Okay, this is what we get after deleting 20. Then 78. So 78 is here. So when we delete 78, so 78 is replaced by the left, from the left subtree. So this is 25. This is 25 should come here, and this creates an empty space. But empty space is not acceptable. So it will look to the sibling. So it has in the left sibling there is nothing available. The right sibling is also only one key. So if the siblings are not in a position to provide or fix the problem, then we look to the parent and pull the key value from the parent and merge the two, connecting childs. So here we can pull the value from the parent, but keep in mind when we pull the value from the parent, then parent should not be like stuck in the kind of, does not violate the property. So that means because the parent has two key values, we can pull one and it will leave the parent with one key value, that is okay. If let's say parent itself is having one key value, we are not allowed to pull from here. Means if we pull, then it will create a vacuum and then we need to do some extra work. But here, because it has two keys, we can easily pull down and merge the two together. So 25 should be coming down, and we are going to merge this together. So what is the impact that we get? We get 10, we get 5, we get 2, 4, here we have 6, here we have 85, and here we get 25, 80, and then 90. So we are done with 78 is out. Then 6. 6 is here. So when you delete 6, it will create a kind of empty node here. So we are going to take a key, because the left sibling is having extra key. We take the key from the sibling, so it will go up, it will go down. So we have 10, we have 4 here, we have 2 here, we have 5 here, and then we have here 85, 25, 80, and 90. So we are done with 6. Then 85, 85 delete. So we will take 85 to delete. So we'll take 80 delete. So 80 will come here, and 80 will delete from here. So it will not violate anything, because every node is having one key and nothing is violated. So we are done with this. Then we look to 10. So when you delete 10, 10 is here actually. So let me first make the tree that we get after deleting this. So we get this at 10, we get 4, we get 2, we have 5, we have 80, we have 25, we have 90. Now 10 to delete, 10 is here. So when you delete 10 from the left subtree, you will find that 5 to be here, and this will create an empty space here. So we look to the left sibling is actually not in position to provide. Then we look to the right sibling, nothing is right sibling. And then look to parent. So parent, when you pull from the parent, so it is, when you pull parent, parent should come here and it will be going to merge. But it will create a vacuum here, because 4 is going to go down and it creates a vacuum. So uh, we will look to the left sibling and right sibling of this node. So there is no left sibling. Right sibling is itself is only one key. So we will pull from the parent and we will merge the two together. So what finally we get 5, 80, and then here we get 2, 4, and here you get 25, and 90. So this is the tree that we get. This is the root node. This is the leaf node. And this is the final answer after deleting all the nodes. So we have seen that how the deletion can be done. So every time when we do deletion, these points to be always keep in mind, and accordingly we have to do the splitting and moving the keys up and down. I would like to show you like in a more cleaner form all the operations that we have done for the deletion. So just have a look here. So this is what we have done, all the stages of deletion, and finally you can look at the final tree that we get after deleting the 10 is this. So we have got 5 and 80, 5 and 80 at the top, and then we have 2 and 4 as a leftmost child, then 25 somewhere here, and then 90. So okay, let me show you like, in a cleaner form. So I have just deleted all the things. So you can see here, this is what we have given to us, and then we delete 82. This is like kind of you see, look at the arrow. This is the first step, and then we have 20, delete 20, 78, this, and finally this is the tree that we get after deleting all the keys which is mentioned here. So I think this is okay to you. Let us take one more example to see that how the deletion is working. So let's move to the next example. Okay, so let's delete uh, this tree. This is of order 3. So order 3 means we need to maintain this number of child will be C lam by 2, that is 2 for every node, and number of key will be 1. So let's start. Delete 25. So 25 to be deleted here. So 25 is the root node. So we will look. We are left biased. So we are looking for the left subtree. 15 is going to replace this, and this will create a empty node here. So it's create the empty node here. So we need to check that how it is going to be fixes. So we'll look to the left sibling. Left sibling is not in a position to pass the value. There is no right sibling for this node. Then we are going to pull from the parent. So the parent is going to pull here, and this 10 and 12 is going to merge. Means this is pulled here. This 10 and 12 are going to merge here, and it creates a empty node here. So for this, it is going to ask from the right sibling. So right sibling is having two keys. So what is going to happen? It will pass this to the parent, and the parent will come here. We get finally something like this. So it comes like this: 32. Here we have 15. Here we have 10 and 12. And one thing to note also that when we are going to pass this to the parent, then the left subtree of this is going to become the right subtree of this node, which is going to uh, you know going down as a child. So this 30 is going to become the right child of this 30, and then we have 64, we have 55, and 78, and 90. So this is what we get after uh, doing the deletion. Now 25 is done. Then we go for 15. 15 is this one. So when we delete 15, so 12 is going to replace this. So it is still fulfilling all the requirement. Every node is having one key, having internal node having two child. So this is done. Then we did 32. So 32 is this. So let me also draw the tree after deletion. So we will get actually this one. So the tree will look like this after deleting this 15. So 32, this is 12, this is 10, this is 30, and 64, 55, 78, and 90. Now we delete. Uh, so we are done with 15. Now 32. 32 is this node. So we are going to delete this 32, and it is replaced with 30. 30 is going to become a kind of empty node. So we are looking to fix this. So we look to the left. Left is having no extra key. Then we look to the right, there's no right. We look to the parent. So parent is going to, pull here. So when we pull here, that means we are going to merge these two together, 10 and 12, and this is going to become empty here. So 10 and 12 is going to merge here and it becomes empty here. So when it becomes empty here, it will look to the left and right sibling. There is no left sibling. There is right sibling is there, but right sibling is also having only one key. So what is going to happen? It is going to just pull from the parent and 30 will come down and it is going to be merged like this. So what is going to happen? We are going to have like this 30, 64, and here we have find this merge 10, 12, and here we have 55, here we have 78 and 90. So we are done with 32. Then we have 64. 64 is this. So we are doing left uh, biased. We are using a left subtree 64 to be divided by 55. This will create empty. So we'll look to the left subtree for filling it. So left subtree we have two keys are there. One key is minimum. So okay, we will pass this 12 here and 30 will come down. So what we get? We get something like this: 12, 55. Here we have 10. Here we have 30. Here we have 78 and 90. Okay, so we are done with deleting the node 30. Which one is 64? 64 is deleted. Then we look to 12. So 12 is this node. So if I delete this, so actually it is replaced with 10. So 10 is going to come here. This is going to be empty. Now we have to fix it. So we'll look to the left. There's nothing left. There's nothing right. Means right is there, but it is not having extra key. So we are going to pull this and merge this together. So what we get? We get 55, and then we have 10, 30, and then we have 78, 90. This is our final tree that we get after doing all these deletions. So let us see all the steps in a like more uh, arranged way. So this is the final deletion that you see: 55, 10, 30, and 78, 90. This is the tree that we get finally. And these are the steps. So let me make this clear. So this is the steps one by one. You can just have a look. So after 25 deletion, this is the tree status. And when you delete 2015, it becomes like this. Then 32, 64, and 12. This is the final tree that we get after deleting all these nodes in the given tree. So I believe you have understood how to do deletion operation in the B tree. So this is all for this video. Thank you very much.